Hello. This section is about working with text, particularly being able to classify internet comments as spam or not spam, and internet reviews as positive or negative. In this section, we'll overview the bag of words model for text classification. We'll look at predicting YouTube comment spam with the bag of words and the random forest techniques. Then we'll look at the word-to-vec models and prediction of positive and negative reviews with the word-to-vec approach and k-nearest neighbor classifier. In this video, we're going to look at the bag of words model. But first, we'll answer the question of what makes text classification an interesting problem. The classification and other machine learning techniques normally require each example in the dataset to be represented as a vector. For example, consider the famous iris flower dataset. This picture is a single individual of the iris versicolor species. If we measure the flower's petal length and width and sepal length and width, we might get enough information to be able to determine its species. The dataset also contains examples of Iris setosa and Iris virginica. Each example in the dataset has these same 4 measurements. Each has a 4-dimensional vector. Overall, there are 150 examples, 50 of each species, and we can fit a decision tree or some other model to predict the species of a new flower given these 4 measurements. The underlying theory is that examples in the same species will have similar measurements. There are different definitions for similarity, but we can think of similarity as closeness in a graph if each point is a flower. Here is such a graph showing sepal width versus petal width. Flowers of the same species will have similar measurements. If we have no way to measure similarity, if, say, every flower had different measurements, then there'd be no way to use machine learning to build a classifier. Now, consider text. What makes the first pair of phrases similar and the second pair dissimilar? If we have no answer to this question, we cannot build a decision tree or random forest or anything else. An obvious answer to what makes the top pair of phrases similar is that the phrases use some of the same words. For example, the words subscribe and channel. While the second pair of sentences have fewer words in common, just very common English words like to and the. So if we can somehow make a vector of numbers representing each phrase so that the top pair is more similar according to those numbers than the second pair, then we can use a random forest or another technique for classification, in this case to detect YouTube comment spam. The bag of words model does exactly that. It takes a phrase or sentence or document and counts the number of times each word appears. We use the word bag because in computer science, a bag is a data structure that keeps track of objects like an array or list does, but in this case, the order is not important. And if an object appears more than once, we just keep track of the count rather than keeping all the repeats. So for example, in the first phrase from the previous slide, it has a bag that has the word channel with 1 occurrence, PLZ with 1 occurrence, subscribe 2 occurrences, and so forth. Then we collect these counts in a vector, 1 vector per phrase, or sentence or document, depending on what you're working with. Again, the order that the words appeared originally doesn't matter, and that information is just lost. The vector can just as well be sorted alphabetically, as long as it's done consistently for all the different phrases. But we still have a problem. Each phrase has a vector with possibly different columns, because they have different words and a different number of columns, like in the top 2 tables. If we make a larger vector with all the unique words across both phrases, we get a proper matrix representation, with each row representing a different phrase. Notice the use of 0 to indicate that a phrase doesn't have a word. If we want a bag of words model for lots of phrases or documents, we can gather all the unique words that occur across all the examples and make a huge matrix, which would be n by m, where there is n number of examples and m number of words. We could easily have thousands of dimensions compared to the iris 4-dimensional model. The bag of words matrix is likely to be sparse, meaning mostly zeros, since most phrases don't have most words. A variety of different processing steps we can do when building a bag of words model. You may see any combination of these listed in practice. Finding out what works best for your particular data requires some experimentation. One more variation is a little more sophisticated. Normal word counts can introduce a problem. The problem is that long documents will have a higher word count, generally, but we probably want long documents about some topic to be considered similar to a short document about the same topic, even though the word counts will differ significantly. Furthermore, we may want to discount very common words and boost the rare ones. The solution is to record the relative importance of each word, rather than its raw count. This is known as TF-IDF, or term frequency inverse document frequency, which measures how common this word or term is in the document, but it penalizes it if it's common in all documents. We use logarithms as well to ensure that long documents with many words are similar to short documents with the same words. TF-IDF has 2 components that multiply. When TF is high, the result is high as well. But IDF measures how common the word is among all the documents and will penalize the common words. So a word that is common in other documents will have a low score, regardless of how many times it appeared. This graph shows that if document frequency is low, meaning it's a relatively rare word, then the score will be high if the word appears frequently in this document. But if the word is common across all the documents, then it's irrelevant how common it is in this document. Its score is going to be low regardless. Thus, the formula exhibits exactly the behavior we were looking for.